guess we'll get started. So I haven't graded your midterms yet, but I'll be doing that probably during lab. I was just waiting for a few stragglers, but hopefully they look okay. Are there any questions or anything before we get started? Where's your class today? I was just wondering where the rest of your class is. Well, y'all are the loyal ones. All right, so we're starting chapter 5. So we have chemical reactions and stoichiometry, so pretty important chapter. So just starting off, so we have kind of physical versus chemical changes. And so just to kind of recap, so a physical change is a change that alters the state or appearance, but not composition. So you're not going to be rearranging any atoms or anything. All you're going to be doing is kind of disturbing those intermolecular forces. And so one of the substances that is an awesome example of this is, of course, water. So you can see water in the solid state as ice. And then you take that ice out, let it sit out on your counter, it starts melting. So that would be a physical change. So melting. You could also, dissolving is another example of a physical change, just FYI. And so you can have that water sitting on the counter, and so the molecules would look like this. So we said that they would have some more degrees of freedom, be able to slide past one another. And then so we can keep adding energy, and we would see that, right? You heat your water on the stove now, it starts to boil. And so then now those molecules are further apart, and so we've gone from a liquid to a gas state. So of course, other things that would be physical changes are obviously like ripping, tearing, or breaking something. Again, you're not altering the physical change, just changing the size of the particles. And so we'll be looking at kind of chemical changes in this chapter and how to write those chemical changes. And so a chemical change then alters the composition of the matter. And so we'll learn that matter is neither created nor destroyed, but instead these atoms just rearrange, transforming the original substances into different substances. And so we're probably all familiar with iron rusting and what that looks like. So you start off as iron metal atoms, and here's our iron nail, and then it would react with our oxygen, so plus O2 in the atmosphere. And so again, you're not doing anything crazy, just rearranging the atoms now. So now they would rearrange to form this iron 3 oxide, which would be rust. And so usually these chemical changes are not reversible. I'll put usually not reversible, or at least not readily. So sometimes you can get a reaction to go in reverse. Maybe if you apply like a voltage, for example, sodium reacts very readily in water, but then you could recover sodium metal back out by applying a current, like to sodium chloride, so that would get sodium back out. And so let's see how we want to write these chemical reactions. So again, they just involve the rearrangement, and so usually we write the reactants, so this will make more sense as we look at an actual reaction. So reactants always go on the left side, products are always on the right side, and there's usually this arrow here, so if it's just this kind of single normal arrow, that just indicates that it goes to completion. So if you could have other sort of arrows. So if you have something like this, this indicates equilibrium, so your reaction would not be going to completion. But for most of our scenarios, right, we're just looking at our simple product arrow. And then so when we write all the reactants and products out, we also want to identify the state that they're in. And so looking at this one, so this is a combustion reaction. And so we'll look at, so what is, let's just look at what a combustion reaction is. And so a combustion reaction, you can always tell that it's a combustion since you have some sort of organic compound, so has carbon, hydrogen, and oxygen, although sometimes oxygen. Then it reacts with O2 in the atmosphere. And then the products of a combustion are always carbon dioxide and water. So if you see those two products, that's a usually good indication. But going back to what we want to show here, so we have our first reactant, so this is methane, so CH4, so you just start out by writing out the formula for each kind of reagent you have in there. So the appropriate formula for methane plus our oxygen, and then gives us carbon dioxide plus water. And so looking at this one, this is an unbalanced reaction, so we'll kind of look at what that means. So all this is doing right now in this statement is kind of identifying our reactants and then our products. And then so we want to put our states. So once you write the appropriate molecular or ionic formula, then afterwards you put the state of it. So most of your reagents, they're either going to be aqueous solutions, so you've kind of seen that in lab, like you know, your strontium chloride or sodium chloride. It's in that little bottle. It's made up of a little solution of it. So normally, right, those reagents would be solid, but it's easier to add kind of two aqueous solutions together, so then they have a medium to react in. Or we can indicate whether it's a solid with an S, liquid with an L, or gas with a G. And so that's all we've done here. So methane's a gas, so you have a G. Oxygen's a gas, so a G there. Carbon dioxide's a gas, and then water is a liquid there. And so normally, we'd also want to balance our equation. So right now, this is just unbalanced, but that's kind of the next step. So the relative numbers of reactants and product molecules that are required, so we need to balance our equation. And so once we have a balanced equation, then we can use that balanced equation to determine kind of the weights of our reactants and products that can be made. And so this is what I would say like 95% of what chemists do, especially benchtop chemists, right, all day, every day. So you're setting up reactions, so you're just weighing stuff out and figuring out how much product you should get, and then running the reaction. So super important skill. And so when we balance these reactions, or rather why it works out, and so again we said that we're not destroying atoms, we're not losing any, we're not magically creating any. And so this means that it follows our law of conservation of mass. And so this also means that the amount of every substance used and made in a chemical reaction is related to the amounts of all other substances, and we'll see that. And then we also want to be able to balance the equations by balancing our atoms. So we'll make sure that they're the same number of atoms on the reactant and product side. And so this is just called stoichiometry. And again, super important, big happy face. So you want to be able to do this forwards and backwards in your sleep all day, every day. So let's look at how to balance this equation here. And they did it for us. Let's kind of start over. And this is how you would approach kind of every problem. So again, let's just say they could even give you the problem really generally and just say methane was burned in a combustion reaction, you know, how much carbon dioxide was produced, whatever. And so you would have to know what a combustion reaction is, what the products are going to be, and how to write everything. So you just want to start off with just writing out the appropriate formulas for all our substances. So again, just methane plus oxygen gives us carbon dioxide plus water. And then, so to balance it, we just want to make sure, do we have the same number of atoms on each side? And so usually you want to start with the elements that are kind of not involved or maybe involved in the most things, and then leave the solo ones like oxygen towards the end. So I'd kind of start with carbon. So we have one carbon, so that's okay. And you could even set up, you know, a little bookkeeping for yourself. You have carbon, carbon, so one, and then let's look at hydrogens. So on our reactant side, on our left side, so it looks like we have 4. And then on our product side, we have 2, so that's kind of an issue. And then let's look at our oxygens for a second. So oxygen, we have 2 on the product side, or excuse me, 2 on the reactant side, and then 3 on the product side. And so the next part, again, is kind of like a guess and check. And so I'm seeing, all right, I need some hydrogens. So I'm going to start by just trying to add a 2 here. And so you balance the reaction by adding coefficients. So you're not going to change the formulas, right? Because your formulas should be set. You know what the formulas are from all the practice you've done. And so now we just want to use coefficients to balance it. And so I'm going to go ahead and try to put a 2 in front of our water here. So now that distributes it, right? 2 times 2 is 4. So now we have 4 hydrogens. And then I'll just do a recount on our oxygens since that changed it. So now we have 2 plus 2. So now we have 4 oxygens. And okay, so now our hydrogens look good. But now our oxygens are off. But again, we kind of save this for the end. And oxygen's by itself, so we could just add a 2 here. So 2 times 2 is 4. So now we have 4 oxygens. And so now, you know, just double check yourself, double check your accounting. So it looks like we have the same number of atoms on each side, so our equation is balanced. And then, so what is so important about reaction stoichiometry? Well, it tells us a lot of different things. So we know, right, how much product we're going to get. It tells us the appropriate ratios. Right, this is basically our recipe for making our chemical cake, we'll say. So just like you have a recipe for making a cake, there's a certain ratio of flour to sugar to eggs and liquid to dry ingredient ratio. So same thing with our reaction stoichiometry. And so we want to know the relative amounts so we can, you know, weigh the appropriate reagent amounts out and put it into the flask, and then also, of course, how much product to expect so we know, you know, what kind of yield we got, how is everything coming. And so let's look at what this balanced equation says. So they gave us a balanced equation. We could double check it. So 2 times 8, so we have 16 carbons, 16 carbons. 2 times 18, so that's 36 hydrogens. 18 times 2, 36, so that matches. And then for our oxygens, so 25 times 2, so 50. And then 16 times 2, so we have 32 plus 18, so 50 oxygens on our product side as well. So everything's all balanced. And so again, this is just ratios. So we could say this is 2 individual molecules of octane reacting with 25 molecules of oxygen to give us 16 molecules of carbon dioxide plus 18 molecules of water. Or we'll look at moles. So we've kind of touched on moles before. We haven't quite defined moles, but we could also say this is a mole-mole ratio. And we'll actually be using moles every time we talk about this chemical quantity. We've kind of mentioned it before, that the periodic table corresponds to the molar molecular weight, and so that's why our mole is relevant. So again, if we say, now we have 2 moles of octane reacts with 25 moles of oxygen to form 16 moles of CO2 and 18 moles of water. And so don't forget, right, we can figure out our molecular weight, our molar weight just from our periodic table. So if we want to know what 1 mole of water weighs, then again we look at our periodic table, just add up everything, and that gives us our grams per mole. So we have 1 for hydrogen, so that's 1 gram per mole. Let me pull out my calculator. And we could do 1.008 times 2, since there are 2 of them in H2O, plus our oxygen mass, so 15.99. And so we could say, right, that we know 1 mole of H2O then has a mass of 18 grams. So just keep that relationship in mind. All right, so let's look at stoichiometry and kind of what to do. And so I think the easiest way to relate it is with cooking. And so I keep telling people, if you can understand cooking stoichiometry, you can understand chemical stoichiometry. You just have to plug in all the random variables for chemicals instead. And so let's look at our pizza recipe here. And of course, the number of pizzas we can make depends on the amount of ingredients we have. And so this is our balanced chemical equation for making a pizza. So we have 1 crust plus 5 ounces of tomato sauce plus 2 cups of cheese give us 1 pizza. And so we could express this as just a proportional relationship. So we have 1 crust of 5 ounces to 2 cups to 1 pizza. So this would be kind of the same as our mole-mole ratio. So again, we can go back and say we have a 2 to 25 to 16 to 18 mole ratio. So that's all we're saying here. And so the nice thing about this is then we can scale it up. So let's say, right, we had 10 cups of cheese then and excess ingredients. And so you could set up your dimensional analysis or proportion. So we have 10 cups of cheese, and we know that 1 pizza requires 2 cups of cheese. Notice how cheese cancels out. So 10 divided by 2 gives you 5 pizzas. All right, so let's try this with s'mores and kind of go through all the types of problems you'll see, and then we'll do chemistry examples. All right, so let's start off with our balanced equation for making s'mores. So we'll start off with 2 graham crackers. I'm going to abbreviate graham crackers. So 2 graham crackers plus 1 fat marshmallow. Can't draw it all. Plus 1 giant marshmallow. Plus, put 3 Hershey's chocolates on there. So plus 3 chocolate pieces. So that all gives us 1 s'more. And so let me give you some other information. And so this would be like your molecular weights. So of course you can't go to the periodic table and look up what a graham cracker weighs. I'll tell you that 1 mole of graham cracker is 55 grams. One marshmallow is 73 grams per mole. And a chocolate is 15 grams per mole. And so the first question is kind of, so thinking back to our law of conservation of mass, so we said, right, mass is neither created nor destroyed. So can you figure out then what is the mass of a s'more? So I'll give everyone a minute or so to think about that.
Oh, that's.
So I see answers in the chat. We have an answer in class. Yeah, or at least that's what the chat got. So I haven't added it up myself. We're just looking at the law of conservation of mass here. So first of all, let's just make it clear that in your balanced equation, where do I want to put this? So in our balanced equation, we know that the total mass of the reactants has to equal our total mass of products. And again, that makes sense. So if we were to quantify all our products, so sometimes it can be difficult to quantify. You know, for example, in our combustion reaction, if you're forming a gas, that could be difficult to measure. But if you could measure the total mass of everything, it would be the same. And so for our s'mores, and again, it makes sense when you're kind of building the s'more, but you can get your molecular weight then just by adding up all the components. And so just so everyone's on the same page, since we have 2 graham crackers, be 55 times 2, plus our marshmallow, plus 15 times 3 for our 3 chocolates. Again, pretending that this is our molecular weight of everything. And so looks like everyone got the 228. And so we could also say, right, that 1 mole of s'more is 228 grams per mole. So now let's look at what other types of problems you might get. So let's start with a simple one. But again, kind of makes sense. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 students, I think, total live. So if I have 10 students and want to make s'mores for everybody, so how much of each reagent, or I guess ingredient, will we need? So I'll give everyone a minute or so to think about that. Oh, we can just do moles, although I like what you were thinking. And again, if you didn't hear it, so the question in class was good. So the question was, should we give it in grams or moles? So I didn't specify, so we'll just stick to moles for now. But eventually you want to be comfortable kind of giving it your answer in any form. So moles, grams, and so that's what you'll be doing in chemistry. You know, how many moles of a product will you get? How many grams is that, etc. Do you have an answer? Or?
I think so.
Or let's just wait like another minute for everybody. Looking for the chat. So what did we get in class? Go for it.
20 moles of graham crackers, 10 moles of giant marshmallow, and 30 moles of chocolate pieces?
Exactly. And so this seems easy right now. So we could set up our either proportion. So we could set up, right, we have 2 graham crackers are needed for every 1 s'more. And we could set up a proportion, so we want to make 10 s'mores. Solve for x. You could also set up with dimensional analysis. So if I want, so I have 10 s'mores, and you want to get to graham crackers, you could put up a conversion. There are 2 graham crackers in 1 s'more. And so, of course, that would also give you 20 graham crackers. And so just like you said, so you would have 20 graham crackers, 10 marshmallows, and 30 chocolates. And so again, take the time to appreciate how to get that, which is simple. Again, setting up a proportion, setting up your dimensional analysis, because right now this seems nice and easy, and it should kind of feel easy. But as soon as we do real problems and then you see like a 1.2 or something, I don't want anyone to freak out and forget what the heck we did, right? So the same mathematical concepts will apply, you know, either set up your proportions, set up your dimensional analysis, whatever way works for you, but just kind of make sure you have that solidified. All right, so let's look at kind of the next type of problem. And so now we can, again, kind of compare things with mole-mole ratios. So if I have 115 chocolate pieces, and excess marshmallows, how many graham crackers do I need? And I should also add, and how many s'mores will you make? So do we have answers? What'd you get?
So I got 76 pieces of chocolate, or 76, moles of chocolate. 0.666 per piece.
You mean graham crackers?
Oh, graham crackers, sorry. Misspoke. Then I got, oh, sorry, for the s'mores. Would anyone else like to take a shot? Oh,
I think you had said it, but I just kind of missed it.
no, I didn't say how many total s'mores yet. I just said chocolate. Graham crackers, why do I keep saying chocolate?
So we get set up, and I see it in the chat. So I see 76 graham crackers and 38 s'mores. So we could set up our proportion, right? So we have 115 moles of chocolate. I want to convert to graham crackers. And so we can go back to our balanced equation. So we have a 3-to-2 ratio of chocolate to graham crackers. I'll put chocolate on bottom, so it cancels out. 2 graham crackers on top, and so that should give us the appropriate answer of 76. So times 2 divided by 3. So that gives us how many moles of graham cracker. And then we could either use our ratio of chocolate. So again, setting up our mole ratio of chocolate to s'mores, where we have our conversion. So 3 chocolates are in 1 s'more, or we could have compared it to graham crackers. So either way, so 76.6 moles of graham cracker. So finding out s'more, so that would be a 2 graham cracker ratio. So either way, you should have gotten 38.3 or so, or 38 full s'mores. So did everyone get this? So feeling good. So we should feel good about this. So again, make sure you're setting up your ratios so when the funky numbers come, you won't panic. So let's start looking at other types of problems. So we're pretty comfortable with this mole stuff. Actually, I want to hand out this handout in a second. And so this is super useful. So this kind of tells you how to get where. Let me hand it out. So this is just a mole highway shamelessly stolen from Everett Community College, but it's super useful. I mean, obviously you should use your dimensional analysis, but sometimes it's good to look at this just to kind of remind yourself. So of course we have our moles. We can get that from our balanced equation. And then once we get our moles, if we want to go to mass, we can multiply by our molecular weight to get grams. And that makes sense because our molecular weight is given in grams per mole. So if we have mole amount, right, moles would cancel to give us grams. If we're the other way, so we can have grams, then divide by our molecular weight. That gives us back moles. But we always have to compare mole-mole ratios. Or at least that's the best thing to do. You could technically do other ways of mass balancing, but just let's keep it simple and just always go back to moles. Again, I say that's kind of our safe space that lets us compare things, again, back from our balanced equation. So now kind of practicing what those questions would look like. Oh, that is not. So if I have $333 grams of marshmallow, how many grams of chocolate would I need to fully react? So see if you can figure out how you might approach that. Do we have an answer yet? Let's see, some nods. So let's just go through together. So what do we have to do? So we have 333 grams of marshmallow. So what do I need to do first? So divide by what? So divide by our molecular weight. And so that makes sense. So 77 grams per mole. So if we're dividing, 77 goes on bottom, 1 mole on top. And so let's see what that gives us. So then this means that we have 4.32 moles of marshmallow. Oh. Oh, no, I thought I heard 77 for some reason. So 333, I'll do that again. Divided by 73. So 4.56. And so now what do we do? That we have moles of marshmallow.
Convert that to moles of chocolate.
So convert that to moles of chocolate. So good, so we could look back at our balanced equation. So set up our dimensional analysis, and you could write this in one big line. I'm just kind of going step by step right now. And so we know we have, for every 1 marshmallow, 3 pieces of chocolate. So then times 3. So now that gives us moles of chocolate, right? But then what did our problem ask for?
Grams.
So grams, what's the last step?
Convert it to grams of chocolate.
So convert it, so multiply it by its molecular weight. Then I have to look back, so we said chocolate was 15 grams per mole. So now 13.68 moles. Chalk times our molecular weight, so 15 grams per mole for chocolate. And so did everyone get like 205 grams of chocolate? Any question on this problem? Y'all feel good about it? So let's try the next type of problem you'll see. So these have been, fairly straightforward. We just kind of assume we have excess reagents. But you'll also encounter what's called our limiting reagent problem. So that'll be 5. And so for these limiting reagent problems, you essentially have to do the problem kind of twice and see, well, which one is going to run out first. And so let's see what I mean by that. I apologize. Like getting over a cold, and I guess by the time I got to your class, my voice is dying. All right. So we have 423 grams of graham cracker. And 410 grams of chocolate. And we'll say excess marshmallows. So what is our limiting reagent? And how many s'mores? So I'll give everyone a couple of minutes to look at that. Do we have an answer of who our limiting reagent is? So how should we start this problem? Yeah.
Figuring out how many moles we have of each.
All right, let's do that. So let's find our moles. We could also just go ahead and figure out how many s'mores each one would make. So we could start with our graham crackers. So we have 423 grams for graham cracker. And then so we want to convert it to moles. And so what do we say the mass of one graham cracker was? So 55, so we can divide by 55. And so once we get there, so that gives us moles. And so then we could set up our mole-mole ratio. So we have, for every 2 moles of graham crackers, we have 1 s'more. So then we could set this up to give us moles of s'mores. So let's see. So 423 divided by 55 divided by 2. So I get that we can make 3.85 s'mores from our 423 grams of graham cracker. And so now we could do the same for chocolate. So 410 grams of chocolate. What was our molecular weight of chocolate? So 15. So divided by 15, so grams per mole. So now that gives us moles of chocolate. And so I want moles of s'mores on top. We need 3 chocolates in every s'more. And so now we can punch that in. So 410 divided by 15 divided by 3. And so I get that we can make 9 s'mores with that. And then so for this limiting reagent problem, you're trying to figure out who was the least. And so what's our limiting reagent? Which one will run out first?
Graham crackers.
So then our limiting reagent, graham crackers. All right, pretty good. And then kind of the last type of problem, we'll do this. And so this could be worded a couple of different ways. Either the problem could make you kind of figure out the theoretical yield. So let's just say and so let's just define something. So if we have, right, our theoretical yield, all that is, so like if you ever have a problem that says like, what's the theoretical yield? That's just what you expect to make from your mole-mole ratio if you have, right, 100% recovery of product. And so we could say, we'll do a really easy problem. So we expect to make, and let's just say we were looking at this previous problem, and so we were expecting to make, let's just say, 3.8 s'mores. So that was our, again, our theoretical yield. So we have this amount of everything. We should make 3.85 s'mores, but we broke some and only made, I don't know how we made 2.5 s'mores, but that's fine. So we only made 2.5 s'mores. What is our percent yield? And we'll just do this one together, since we haven't talked about percent yield. So all percent yield is it tells us how much, like what percentage we got back of what we expect. So the formula for that is just actual. So basically whatever you do your reaction, you filter it, you do all your manipulations, and you weigh it out. So how much of that beautiful product did you weigh out? So that's actual over your theoretical. And then, of course, times 100 to make a percent. So in this case, our actual was 2.5. We expected to make 3.85. So then what do we get for our percent yield?
64.9%.
64.9, so that's not too bad, not too great either.
Maybe what happened, the reason they only got 2.5 is first they accidentally ate the remaining 0.8, and then after they made the finished product, they accidentally ate half of it. So that's why we only have 2.5 points.
Yeah, I mean, the possibilities are endless of what could go wrong. And of course, in the lab, right, that's where you start writing, especially once once we start doing more manipulations, then that's where you're gonna write what went wrong, and that can be anywhere from I tripped and the product blew away, which I've seen happen, or oh, I lost some, while transferring, blah, 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 blah. And so, of course, you should.
Turns out the marshmallow was more combustible than we thought.
Exactly, so you don't know what happened. And so you should never have over 100% yield. So if you were to ever get like 100%, over 100%, usually that means,
you eat the laws of physics.
usually it means you contaminated it, it's still wet, so something is up, or it's impure, it's not what you think it is, so something is up. So you would never be perfect and get 100% yield. Plus reactions, we say they go to completion, but there can be side product, gunky things, etc. And just as like a FYI, so organic reactions, you want them, at least ideally, if you're doing grad school, you want them to be like 90% yield or so. Like that would be really good if you had a 90% yield. But then like for inorganic reactions, anytime you're throwing metals at things, you might only get like a 50% yield. So it really depends on your field and your reaction. All right, so now that you did this with s'mores, you're ready for chemistry, right? And you'll do it perfectly.
So when do we get to eat the s'mores?
Unfortunately, I didn't think about bringing s'mores. So I guess
You could use the Bunsen burner to make them.
we could have, I didn't think about it.
Really dropped the s'more on this one.
I know.
That's why we only have 2.5. Only that 65% reaction yield.
All right, so let's look at this kind of mole conversion. So this should feel like a recap. So again, you just want to do your mole ratios, so be able to set them up. So let's just do this. I know it gives us the answer, but let's do this practice one. So how many moles of CO2 form if 22 moles of octane are combusted? And if I were you, I would just look at this balance equation. Let's get rid of this for now. So we'll give everyone a minute or so. Yes.
Got it.
I'm giving everyone another minute or so. Still see punching and typing. Looking at the chat too for answers. Let's see. So let's hear them, or let's see what you did. Since
200, as it's one significant figure because of the conversion rate in the reactor.
no, the conversion wouldn't count, or else we would have like no sig figs ever.
Exactly.
Yeah, that's not gonna work. So you have 3, right?
Oh,
From your-
okay, if that's the case.
Yeah, because those are just mole ratios.
But you're sure, right?
Yes. I would literally destroy it. All right, so just like before, I'm just gonna redo it even though they drew it out for us. So we start with what we know. So we have 22 moles of octane. And then we just want to look at our balanced equation. And so, right, I'm interested in CO2 and comparing that with our octane. So you can see they're in a 2:16 ratio. And then I'm going to put moles of octane on bottom since I want that to cancel out. And then so 16 moles of CO2 on top since that's what we're interested in. And so I'll plug it in just so we know that the example is correct. So 22 times 16 divided by 2. And that gives us our 176 moles. I see the chat also got that. And so just like we did with our marshmallow, we should be able to do the same thing with real chemicals. So given your moles, so then we could plug this in and multiply it by the mass of CO2. So let's try this new problem. So now it says determine the mass of carbon dioxide produced when 3.6 times 10 to the 15 grams of octane is burned in excess oxygen. So we don't need to worry, at least, about trying to find our limiting reagent. So I'll give everyone some time. So how do we go from grams of octane to grams of CO2? So what are some things we might need to determine maybe before we start diving into all these calculations? Yeah,
How much the mole of each chemical is?
exactly. So let's calculate that first. So let's do CO2 and figure out what its molecular weight is. So again, we can just go to our periodic table and add everything up. 12.011 for carbon, 15.99. So you should get about 44 grams per mole or so, depending on how you round. .44 grams per mole. And then what do we get for the mass of octane here? So 12.001 times 8 plus 1.008 times 18. So do we get like 114 or so? So I see 114.26 in the chat. So something like that. I'll just put 0.26. You could also look it up, but it's good practice to at least like know how to calculate this. So now we have, right, our molecular weight here. And so what's our next step? What should I do? So they gave us a balanced reaction at least, so that's good. We don't have to worry about that. So what do I do with this 3.6 times 10 to the 15 grams? What do we do with our s'mores when we have grams? So it doesn't matter that this is, you know, to the power of 15 or whatever. What's just the step? So we have grams, so how do we convert to moles? So look at your dimensional analysis. So if we were to multiply it, right, you would get like grams squared over moles, so that'd be kind of weird. And we want moles. Yeah, because if we divide, moles will go on top, grams on bottom. You also have your mole highway sheet to remind you, right? So mass to moles, and then it tells you with the little arrow, divide by molecular weight to get moles. So have this handy, right, to kind of jog your memory, help you. And so let's see, so let's divide now by our molecular weight of octane, because that's what we're given. And so 1 mole will go on top, is 114.26 grams on bottom. Right, so now my grams cancels. And so we can calculate that. Let's just calculate that so we don't do one giant thing, which again we could do, but let's go step by step. So now we have a ridiculous amount of moles. So we have 3.15 times 10 to the 13. So that's going to be moles of octane. And so let's see. So now that we so we have moles. We have our balanced equation. So how do I go from moles of octane to moles of CO2?
Why is it called octane and it has no oxygen in that?
That's its name for it.
Oh, sorry.
Because it's oct for 8.
Oh, oct. I thought you were saying ox. There we go. Sorry, that makes more sense.
So then I see in the chat, multiply it by the ratio. So exactly, right? Go back to your balanced equation. So we have 16 moles of CO2 for every 2 of our octane. And so again, we could have set this up in one big line, but I just stopped to gather. So now we have moles of octane. We want moles of CO2. So we could put CO2 on top, octane on bottom, and then just grab the numbers from your balanced equation. So again, 16 over 2. And so we can just, that's the same thing as multiplying it by 8. So do we get like 2.52 times 10 to the 14 moles of CO2? So I see a nod. So 2.52 times 10, 14 moles of CO2. So now we're at moles of CO2, except it asked for mass in grams. But we calculated, right, the molecular weight. So we have its molecular weight, grams per mole. So what's our last step?
Convert moles back to grams.
Yep, so we just need to multiply. So again, we have moles, so we multiply it by grams over moles. Moles will cancel to give us grams back out. And so we'll just do that. So again, times our molecular weight, and you have your highway. So it reminds you, okay, how do I go from moles to grams? Oh, yeah. All right, so I think we're out of time for today. So we'll keep practicing on Thursday, doing more stoichiometry calculations, and then seeing what else is in chapter 5. And then, so this week's lab should be pretty fun. It's chemical reactions, so I'll have those printed out. And then if you're doing it online, there should be like links to different YouTube videos that do the different sections of the reaction. And so just let me know if you need help with that. Oh, and I have a homeless homework. I can't tell whose handwriting it is, so I'll leave it out here for people to look at. All right, thanks, y'all. So I'll see you in a little bit for lab, and then I'll hang around on stream in case there are any questions. Otherwise, I'll see y'all on Thursday. It's kind of up to you, because either you could just like re-emphasize the 3D structure, like I would be okay with that, like for, like for this one, drawing out the wedges and the dash. Or if you wanted to like, take your colored pencil and draw it in, that would also be fine, but I kind of leave it for you. Hopefully by Thursday is my goal. Yeah, so it's all, is. Yeah, so it's under week 6 this time. And so the lab has like part A, blah, 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 blah. So you just follow all that, and then if you click here, there should be a PDF document. Yeah, and then just let me know if you need help. Oh, I'll take it. Sweet.
So, is there like an idea of like, if we miss a lab, will it be okay? Or,
Yeah, you would just do it online.
okay, awesome. I lost one of my contacts and my head really hurts.
Oh
Because
no.
I can't see it at all.
Yeah.
So, I don't think I'd be much of a safety, I'd be a safety hazard to the lab. So I won't see you today for lab.
Okay. Yeah, everything. This lab, it's a little funny just because there's different reaction types. But if you look at YouTube, it kind of tells you like where to start and blah, blah,
okay.
blah. But they're all there on YouTube, so yeah, it's okay if you need a miss. The curtain's ditching you.
Yeah, I'm aware. I said I'd try.
Alright, any questions on this stream? Otherwise, I'm gonna stop streaming. So thanks again, chat, for being on top of things. All right, thanks again.